Welcome everybody to another Bitcoin Core PR Review Club. Today we are checking at PR number 28165, which is basically a prelude to BIP 324. So, like for those who are new, we have been talking about BIP 324s in past review clubs, and you might have like heard about it. So today we are checking a PR by Peter Wheeler, which recently got merged in Bitcoin Core, and it's about certain structural changes that he does into the net.cpp and net.h file, and which are quite good to understand how the internals of net processings and network infrastructures are working in Bitcoin Core. So Stratosphere gonna guide us through the PR, and she has this amazing note today. So really excited to join in. Stratosphere, all over to you.
Awesome. Yeah. So we'll start by just going through the very basics, and then we'll go into the questions, just so that all of us are on the same page.
Right.
Yeah. So we know this, like all Bitcoin nodes, they communicate by exchanging P2P messages, and like you must like know all the like. Can you give me examples of P2P messages?
Like messages like give me a transaction, or like give me addresses, or give me blocks, or stuffs like that, right?
Yeah. Yeah.
I'm trying to find the message enum somewhere in the code, but like go ahead, like whatever you're saying, I'll try to find it in the back.
Yeah. Okay. Yeah. If you get the link, share it.
Yeah.
So yeah, there are all kinds of P2P messages which get exchanged. Like sometimes you send a version message. That is like when you first connect to a Bitcoin node, you send that message. That's the transport protocol. And the node should respond back with a Verac P2P message. Then to check if you're still connected to node, you send a ping message, and the other node would respond with a pong message. So like they're speaking this protocol. That is the Bitcoin protocol, essentially. It's a
Right.
set of rules.
Yeah. So and it defines certain formats and certain message types, and goes like so if you want to have send for a request in the P2P network, you send this data in the network as some raw format, and that's basically the language of Bitcoin.
Yeah,
Right.
that is essentially the protocol. When you receive something, like what response should you make? And all these data is exchanged between nodes in the form of P2P messages.
Mm-hmm.
So that's like the very blood of Bitcoin, like how
Right.
data flows through the network.
Right.
So how do you send these P2P messages? You have to send it over the wire. So you have to make them into a byte format. So that is handled by a class called transport in net.h. So see, the transport converts one connection, sends messages to wired bytes and received bytes back.
Right.
So that conversion is done in this class called transport. And currently, like all the P2P messages which you send on the wire are unencrypted. So any passive observer who could access these wired bytes, they can understand that it's Bitcoin P2P messages being exchanged between the nodes, and they'll be able to like if they get the wire bytes, they can cut message and they'll know what messages the nodes are exchanging.
Right. And that's like the problem of like IP snipping, or like if your ISP wants to like ban Bitcoin nodes running in their region, that's the way they will go about doing it. So that's why it's important that BIP 324 we figure out ways of like obfuscating the regular network traffic.
Yeah, exactly. So this unencrypted transport protocol form, we're going to call it as version 1. So V1 P2P protocol here.
Right.
So that terminology is V1 P2P. And V1, this is what we talked about. Like how do you first initiate a connection with a new node? Like you initiate the connection with a new node by sending a version message, and you wait for the node to respond back with a Verac. That's called a version handshake. And that's the first P2P message which two nodes exchanged.
Right.
After that, everything else follows.
Right. If I'm not wrong, it's at version 2 right now, or some other kind of data, or what is the version message in generally like looks like for nodes?
We can look. It's done push node version. So, like you can see, it's making like this push node version. It's calling push message, and it's
Right.
making this constructing this version message here.
And there is a init proto version that is a constant, and
Yeah,
right, 209. Nice.
yeah,
Okay.
yeah. So that's how you initiate a connection with a new node, and this will always happen. And so we know it's a version message which is going to be sent to the node. Yeah, so we got the version message, and that version message actually it's a CNET message maker. Like it's basically a message. It's not bytes formats yet,
Mm-hmm.
and over the
Okay.
wire we can only send bytes.
Right. So the CNET message maker will contain like the message as a structure form. Can you look at this definition? CNET message
Yeah.
maker. So it has an inversion field, and it has few arguments, and it has
It yeah, it deals with this C serialized net message.
right.
That is the return type. So when we said push message, like when we said this is basically returning what a
A,
C serialized nest
a,
message.
a serialized network message, like whatever type of message that we are trying to create. Yeah.
Yeah,
Okay, so the serialized message is still not enough for the wire. Like the wire format is more byte specific, is it?
uh, I think the C serialized. Okay, so you're asking like where does this thing gets converted into serialized bytes? Actually, it gets
No,
converted in C serialized net message.
so no, I'm asking the transport class is doing more than serialization. Was my question. I thought it was just serializing the message, but looks like message is already serialized.
Yeah, that is not done by the transport protocol. Like the transport protocol should be responsible only for sending receiving messages from the socket,
Right.
right?
So it
The
should not like
serial
concern with serialization. So serialization is
No,
happening somewhere else, I guess.
I meant
yeah.
the transport class which we discussed earlier. No, it converts message to wire format or something.
Oh, let me check.
The transport converts one connection send message to wire bytes and received
Okay.
bytes back.
Yeah, so
So
that is not serialized. Wire bytes is not just serialized bytes, is it?
it is serialized
It
bytes.
is.
It is, I guess. It's the final bytes that will go through the wire as a network message.
Yeah.
Right.
Then why do we need the transport class? Because it's already serialized. Okay, I don't know. I'm just getting confused.
Yeah,
Oh,
whenever you
yeah.
feel
So,
like why a class exists in Bitcoin code, like yeah, that's a really good
yeah,
question sometimes, and will like often learn you towards like the architecture. Yes, but it's always a hard question why a class exists. And
that's a very good question. Actually, Sipa was talking about it in the PR. Like he was
right.
telling the term serialization is very confusing. Uh,
Yeah. So
like,
I think this is a very common design pattern you will find in I think on other projects too. It's a separation of concern. Separation of concerns. Basically, what it does is serialization is different than transportation. If somebody is designing plug and play kind of design pattern, you can have your own or maybe any custom transport class or something like that, you can plug in over there, and serialization is always separate.
That makes sense. Yeah.
Serialization is just converting a message into a certain format. And if you're transporting into TCP or maybe some other transport protocol, you can always plug in that. So this is a modular design, actually.
Right. So if
Yeah,
you look at
right.
the transport class, it also shows like all the functions are virtual, right? So it's an interface class basically.
Yeah. So this
Uh,
transport deals with how things are getting finally sent over the socket. It doesn't deal with making the message into serialized byte format.
right. So it has an API called get received message. So
Yeah.
it will basically like if there is a received message, oh no, it will like receive it from the like implementer itself, and it returns a CNET message, right? And the CNET message says like transport protocol agnostic message container, and ideally it should only contain receive time, payload type, and size. So it's basically trying to like abstract away the transportation layer from the serialization. I guess that's the point of the PR also, and he describes it in the PR description.
Yeah. Previously, we had this both serialization and transport stuff mixed together. So
Yeah.
now this modular design kind of separates both those functions.
Right, makes sense. Okay, let's trace back. Where were we in terms of discussion? We were talking about version 1 P2P structures. So basically now we have a transport class which is like trying to abstract it, but that's going into the PR. Let's talk over the notes, and we'll look back into the PR with the questions. So
Yeah.
yeah.
Yeah. And this is the serialized form for V1 P2P message. Like, yeah, it's unencrypted, right? So this payload will be in an
Right.
unencrypted format. And this thing is the header. So
Mm-hmm.
you have 4 bytes network magic. So that is network magic will define whether you're running it on mainnet or reg test or whatever.
Mm-hmm.
It's
Yeah.
it's fixed for
Yeah, these are constants throughout the network, right? And we can probably
yeah.
find the constant somewhere. It's defined. I forgot where.
Guys, one question for you.
Right. Yeah.
Yeah.
So if you go back to the previous screen, the diagram, what you're saying is payload is not encrypted. The peer-to-peer communication that happens between two nodes, isn't it on SSL or, I mean, what is the problem here? I mean, we are only concerned with the payload encryption or what is that?
This is unencrypted. So like it's TCP connection. So basically, if you run something like Wireshark, you can actually see the deciphered unencrypted message on the screen.
So
Okay,
it's
so
like bare network format that is like in this specific protocol structures. So if you can like read the like the wire stream, but you have to like read it in between that connection, like when it's happening. But if you run a node and in your home, then if you do Wireshark on your like router, you will see that you are doing Bitcoin transactions, or like not even Bitcoin transaction, it's like Bitcoin transactions are coming and flowing through because your node is constantly downloading data. So now like you can like geolocate IP addresses of node runners, and so that's the problem.
And this is essentially the network package, like it's the Bitcoin protocol network packet. So we are not using any other protocols.
Right, and you have to like put it in this way because like the Bitcoin protocol like only understands a message like this, right? So um there is no like SSL connection happening between the nodes, right? So it's all happening in open network, and anybody can connect to anybody. There is no authentication mechanism going on, so there is no way to hide this data. And yeah, so I guess that's answered the question.
Okay. Thank you.
Mhm.
Yeah, so this is just the format. Like it has a network message 4 bytes, the command, and you'll pad it with zeros, whatever length of payload, and checksum, you will double hash payload and take the first 4 bytes, just to make sure that there is no error,
In
like
the
when the
message,
payload
like
gets.
it's kind of like a mac, it's kind of like an integrity of the messages like there, so you get to get sure like no bytes have been lost or anything is corrupted.
It's just an error checking mechanism. There's no
Yeah,
authentication
yeah,
kind of stuff.
yeah. So just to
So
like
that's
clear on the previous question, is like while we are discussing about that visibility problem, we are not like to clear like this PR is not solving that. That's the BIP 324 project, and that's a long-standing project which is spanned over multiple PRs across Bitcoin in Bitcoin Core, and this PR is like the very first of the lot where it's like doing some basic redesigning changes in the net.h and net.cpp before, and creating the groundwork for the remaining changes for BIP 324.
yeah. So BIP 324, it basically introduces a new P2P protocol, and that will be able to send encrypted P2P messages. And
Mhm.
so we're going to call that as V2 P2P here. And so this is the wire bytes format for V2 P2P message. It's essentially have the contents here, the payload thing,
Right.
and like there's a 1 byte header which is for traffic shapeability actually. Like if you set it, you can the receiver, like whoever receives this P2P message would ignore this whole P2P message.
What?
So
I didn't get this part. Okay, this is interesting. What's happening here?
yeah, so like there will be some fixed byte. Like if someone maybe runs some like there will be a fixed pattern based on which Bitcoin P2P messages are sent, right? There will be a
Right.
fixed
Okay.
frequency, fixed
Yeah.
timing.
Hmm.
So clever attackers could like collect all these data and still understand that it's Bitcoin protocol being run because of the frequency at which messages are being sent.
Right. Okay.
So we want a way to be able to like
Okay,
what do
decouple
you say?
from that like decouple from that fingerprint of like uh, so it's happening via like this time frequencies between different messages, so this byte basically delays certain message in a random way, and then you cannot
You
correlate in
can
that.
send a you can send a decoy message. Like I'm
Okay.
sending a message, but you're just supposed to ignore it.
Oh, okay. Okay, so it's a
So you can
decoy
send
message.
like garbage, I guess.
Exactly.
Yeah.
Garbage value or whatever. Yeah.
Yeah, it's
Isn't
like
that
garbage.
banned for like bad for bandwidth?
Yeah, it is. But
Yeah, I
we're
guess
not
like
sending it that frequently. It's just
hmm.
in case of adversarial scenarios, it would be good to have some traffic shaping mechanism.
Okay.
Right.
Okay.
Because like there might be predictable stuff, right? Like the first message could be always to get the seed, node seed, what you call the seeds, right? DNS, the seeding and stuff. So there can be
Yeah.
predictable messages, which like from the pattern you can understand. So I guess.
Right. Yeah. Yeah. So it's not just enough to like obfuscate the payload. It's also, you also have to like decouple from all the other fingerprints that can happen via the protocol. Right.
Yeah.
So like a particular specific header bytes that always reoccur, and timing of messages that happens after a certain frequency. So yeah. Okay. Now I understand. So is
Yeah.
it like, is it gonna be like a policy of the node, like you as a node operator can choose to opt into this thing to like shape your traffic if you are like worried about being tracked, and in expense of a bit of bandwidth, or it's gonna be a global thing?
It's a policy thing. Like currently, the code doesn't
Ah,
implement. Like there's a provision for this, but no one is sending decoy packets. Like we have
right.
not said anywhere we are sending a decoy packet here. It's
Okay.
just optional.
Okay. Okay. Makes sense.
So this orange thing is the contents. It will be encrypted form, and this length will be whatever length of those contents, and then MAC to authenticate it.
Right.
If the authentication fails, like you disconnect from the pair.
Okay, and that's like all the alligator swift. I'm pronouncing it right. Alligator.
Yeah,
How do you say it?
alligator,
Alligator swift.
alligator.
Okay, so
Yeah,
that's like the public key cryptography magic happening behind that authentication part.
yeah. So like we need this stuff to be encrypted, right? So we need keys. So
Right.
how do we get keys? We use it like we get the keys using a form of Diffie-Hellman key negotiation phase, which uses those alligator swift stuff, and so that's how we get the keys. And so this will be the message which is going to be first exchanged in BIP 324 or V2P2P protocol. Before we know that we used to send a version and like we used to do this version
Right.
handshake,
Right.
right? So
But
here,
now there is a whole authentication protocol and setup process that's gonna go on before like sending the messages.
yeah, but that's just a very small initial handshake. After that, the protocol goes exactly as it was before.
Okay.
Version handshake and everything else. There's just a small Diffie-Hellman key negotiation phase happening in the very beginning, just to
Okay.
get the keys.
Okay.
After that, everything else remains the same.
Right. So the
So
behavior of the
I
network remains the same. Yeah, go ahead.
I didn't understand what the MAC is. Is it like a signature on the contents or something? Or
It's an authentication kind of thing.
so is it like a signature on the contents, like so
Yeah,
that okay.
It's called message authentication. I forgot what C stands for.
code.
Message authentication code. So it's like a cryptographic piece of data with which, if you have the message and this piece of data, you can like prove that it came from the right user with the right content that it was supposed to.
So in transactions, that is like the signature, right? Only if you had the public key, you
Technically
could make
it's
it.
like in an abstract way it's similar, but technically
Okay, okay,
it's
fine,
two
fine. Yeah,
different
sorry.
things. Yeah.
Yeah, okay, okay.
Yeah, kind of like like signature but not exactly signatures. Mac, right? Message authentication code, that's what the name separates it out for.
Yeah, it's kind of like a higher level compared to this payload checksum. Like payload checksum would just
Yeah,
detect if there
it's an
are
error
errors.
detection, and this one will like detect it also, like authenticated in all the ways, like it came from the right user and all.
Yeah, it's error detection plus making sure that the message came from the right user.
Right. Okay, makes sense.
Yeah,
So let's
so
pause over here for some time and let's see if anybody
yeah.
has any conceptual question. If not, then we'll go ahead. Okay. So what's
So
next?
wait,
Yeah.
we don't need the content size and all anymore, right? Because the MAC is there. Like
The
earlier,
contents,
no, earlier we
oh,
used to have a size, right? So it's there. Or
that's
length.
still the
Okay.
length.
That's like this. It starts with the first one. Right. It previously used to start with the version. Now it starts with the length.
That's
Right.
right. Yeah.
Yeah. Yeah, because you need to have like the length somewhere. And
Right. Okay.
Otherwise, how will we know where the packet ends?
right.
I mean, you could have defined packet lengths, but I guess that's not efficient. Yeah.
I guess
That's
that's
bad for
efficient, but that's problematic with like those tracing kind of thing. That's another fingerprint, right?
Oh, yes. Yeah. Yeah. Okay.
Yeah. So, but yeah, like if you have to like write byte serialization of any data, you will like this is like the common structure you will start with. It starts with the length because that's where you know when to stop reading from the network socket, right? So you need to know how many bytes to read to get a message, and that's like the first information you need before you start getting the message. And so yeah.
yeah.
That was a good
So we're like,
question. Yeah, it was like it's a good discussion. Often, like in various serialization, we have other data, but if you try to write your serialization format, you will very soon find like you have to like know the message length, and without that, like your serialization will not work. And so that's usually a surprising thing. Like only if you're doing it first time, but then it becomes obvious. So that's like also another interesting side note on this. This is like another problem I faced while like doing one thing. Like if you have like situations where you don't know what's the message size could be, and you don't want that to be visible also in the network, then it becomes very hard to create a serialization and deserialization on top of that. And so yeah, that's why like in general it always starts with the length, or at least like length somewhere before the message field.
makes sense.
Anyway, that's a bit of derail, so let's get back. I guess like we covered the basic part of the theory. The last point was about this transport deserializer. So previously we had a transport deserializer class which was responsible for like getting the message and deserializing the message. And now we have only a transport class which is only responsible for getting the message. Am I right?
For both, like it performs the functions for both sending
Oh,
and
okay.
receiving.
For both sending and receiving, but not the serialization.
Yeah,
Only
no serial.
only transport.
Yeah.
Okay, cool. Makes sense.
I'm also confused by Emil's first question, like where the serialization actually happens. Yeah, I think we'll get into it somewhere here. Oh yeah, we'll go in order.
Cool.
The part wherein you talked about the difference between transport deserializer and transport serializer.
Uh, Sorry.
Sorry, can you come again?
So how is transport serializer different from transport deserializer?
Oh, it's the opposite, two opposite thing. Like one serializes, one deserializes, right? So like okay, so this is like many things that you will see in common in programming is like you have a object in the in your code that represent a structured information, and that structured information is memory, and then you have API on top of that object, and then you have to like pass that object into another computer or in a file. So you have to translate that object into some byte format or JSON format or whatever. And so that's the job of a serializer. And you take the object, serialize into this data that you can just dump on a file or like pass through the network channels. And the deserializer is the opposite part of it. You get a bulk of data, now you have to like recreate your memory structure again so that you can use that data into your code with the APIs and stuff. So that's the deserializer part. So it deserializes the data into its semantic definition inside the code.
Got it.
So you can think of like object to data to data to object and back and forth. And it's done by these two things, serializers and deserializers. Okay. Yeah, then let's move ahead. If any no more conceptual questions, and we start with our real questions. Then okay, let's go.
Yeah. Yeah, our quick definition, like quick basics went to half an hour. So
Yeah, that was nice. That was like actually like good to set the ground, because we are gonna look into code now. So will be good
yeah,
to have the concept in the head while looking at it.
yeah, definitely. So yeah, we'll just start with this question. What are the different net threads? What do they do?
Right. So I just did a basic search of it, and it basically says what they do by their names, right? So
Yeah.
this we have like a message handler thread, then with a DNS address seed, so it looks for addresses, or like it loads the addresses peers from the DNS, so that happens in another thread. I don't know why thread map.port is not like linked anymore. Does it not exist?
No clue.
Okay. Universal plug and play startup and shut down. Oh, okay. If it's universal plug and play, then it's an UPnP thing. I think that's a configuration thing. So that's why it's not linked with the code.
The function is there.
Okay, so yeah, that's like, yeah, use UPnP and stuffs like that. So that's like Bitcoin Core has its UPnP thing, and that's that thread what it starts it. Thread socket handler, that's like the network
What's
socket handling.
UPnP?
Sorry,
What's UPnP?
UPnP is universal plug and play. It's that thing is like, if you don't have, like, I'm hazy on the details, like if somebody is like more like well known on the internet network translator nats and stuffs, like this is where your node can like create a public port that is like accessible from the public network. And if you are running under a Wi-Fi or like a ISP provided internet connection, the you need to like port forward the traffic from your Wi-Fi to local node manually. UPnP is like, you don't need to do that setup. Bitcoin Core will handle that automatically if your Wi-Fi is UPnP enabled. Does that make sense?
Kind of.
Right. Yeah. So yeah, that's like an user level thing and useful, but you can like feature get it, like you can turn off that feature because it's extra code that Bitcoin Core will compile. So if you go to configure.ac and all the feature flags, there is a feature flag called without mini UPnPC, or without mini UPnP, or yeah, without mini UPnP. That's like what disables the UPnP capability. And then you have to manually go to your router, do the port forwarding and stuffs like that.
Cool stuff.
Okay, so then we have socket handler. It's like, I guess, that's like the P2P socket listening to stuffs at 8333 and sending stuffs via 8333.
Yeah.
Then we have open added connection. Yeah, anybody asking something? I guess not. Okay, we have open added connection, and that is like open connections to added nodes. I guess like nodes which are already added.
Yeah. Kind of like inbound stuff.
Ah, right. And open connection to peers, that's like the outbound stuffs.
Yeah.
Okay. Okay. So these are like handles in like two different sets, like two different threads. And
Yeah.
okay. And so for somebody who doesn't might not know, it's just for information, this number of inbound and outbound. So they will like Bitcoin Core differentiates between traffics of other peers among like who are the inbounds and who are the outbounds. And it has like 8 outbound slots and 120 or 117 inbound slots. Or I'm wrong, 125 inbound slots.
It's 117, I guess.
117, right? So total 125 slots of peer connections you can have manually. But I think this is also a policy, so you can like increase this number.
Yep. Not advisable though, but
Okay.
like it just puts stress on the network if you like increase it.
Okay.
And if you decrease it, like you're making yourself vulnerable to Eclipse attacks.
Right. Yeah. We did a very old review club on like different types of like connections, and there are
Yeah.
anchor connections, block only connections. Those are like quite interesting. Somebody, if you're interested, can scour our previous recording and might find one. I forgot in which one we did it.
And like both send and receive is through one port, right? So I think that also puts some strain on the port. Like you can't do multiple things at once, right?
I guess so, yeah.
I actually just asked this question to someone. I'll let you know the answer. like,
Okay.
yeah, or we can like try it after. Like we can look at the ports. Maybe after the recording is done, like we can run a Bitcoin node and look at the ports.
Yeah,
I mean,
totally.
if I do it now, yeah, if I do it now, my IP address, everything will get seen. So
Yeah, okay, makes sense. We can try, we'll try that out.
yeah.
So that's on the threads. And then there is I2P. I think there is also a Tor thread, or like those
Yeah.
options. Okay, that happens like over there. Tor control thread. I wonder why it's not under the net thread section. Maybe like for some reason, but yeah, just
It's a good question. I'm thinking. Is Tor? Yeah. Okay, then yeah, like that makes sense. But then why is I2P here?
right. I guess like they
Oh,
forgot,
okay.
or maybe because it's this library structure is a bit different, like it's maybe spawning from somewhere else, which is not usually where net threads are being spawned from. That's how they wanted to like separate it out, but I don't know.
We'll check into it later.
Oh, another thing, it could be like maybe like the Tor thread is starts by default. You cannot stop it, but I'm just guessing. I don't know, but
Oh,
we'll
like
check
we
it
can
out later.
actually look. Yeah, like it's also like, yeah, it's also kind of related to this diagram. Like we can see where all these net threads get spawned.
Okay, let's see
So
that.
yeah, so this is app init main. That's the first function which gets executed. Like in our OBC reading club, like we did this, right?
Right.
Like all these steps are listed here. I think somewhere around step 12, it's where you start the node.
Right. Oh, nice. So this whole process is also like stepwise demarcated. I
Yeah.
missed that last time. So that's cool to read through. Okay.
Here's the UPnP stuff. Yeah. Anyway, so you have a lot of connection options here, which can be set based on whatever you gave in the configuration file.
Right.
And
I think what would be good is like, can you like or hide the terminal view and increase the size of the letters, like the font size, one step.
how do you do that on client?
Try Control Plus. I'm just
Doesn't work.
doesn't work. Okay, it works in VS Code, but if it's too hard to find, then we can skip. It's already readable.
What? Alt Shift 0.
That is the most random.
It doesn't work.
It doesn't work.
No.
Okay.
Command mouse. No. What?
Maybe right
Okay.
click zoom. Like whoever designed this UI did not thought of this use case, and like, yeah,
It should be in view.
it could be in view. Appearance.
Font size, shift off, scroll down.
Where is it?
Increase font size in all at scroll down.
Alt Shift dot.
Ah,
Oh, thank you so much.
nice. Yeah, this is good now.
Yeah, it's good.
Yeah.
Yeah, so yeah, there's
Okay,
this
so this is
option
where
where
the
all
all the
these
options are being set, right?
and
And somewhere it will
finding,
start a thread somewhere.
yeah, where is convents? Yeah, like this is where a connection manager, like we start, and that's where all the net threads get actually started.
Ah,
Uh,
okay.
okay, that's on line 1864. I saw Tor or something somewhere before.
Maybe just search through for Tor. It will be highlighted here. That start Tor control, I think that's the port. That's the function that starts it. There was a start Tor control. Yeah.
Ah,
And yeah, that function will start this thing. So if you have like listen onion, and that is like this configuration flag, and it defaults to default listen onion. I'm curious, what's the default listen onion? What's the default? It must be a constant. Default is true,
default,
right? Yeah. So Tor basically starts by default unless you do listen onion equals to false or something.
huh? Or is it like if you like specify listen onion without anything, it's
No,
set to
then
1?
if you don't specify it, it will be set to 1, and by default it's set to 1. So you will only those. So there are certain configurations in bitcoin.conf which are like that. That if you don't specify, it will be default set. You specify when you want to disable it specifically. I guess it's
Oh,
one of those categories.
okay.
There is another configuration related to onion is like only net onion, but I don't know, we should find it right now. It can be another rabbit hole on its own.
I mean, that's like setting only net equals onion.
Yeah, so that's like your only onion net will be set. So no clear net, no I2P, nothing. And clear net and onions are gonna start by default. If you have a Tor server running, like if
Yeah.
you have Tor installed and running, Bitcoin Core will automatically identify that, create an onion address for you, and even start a hidden service at the background. And I think previously it was done manually. Now it does automatically does that. So you are already listening as a Bitcoin hidden service in Tor address, and any node can connect to your node via Tor also.
Yeah. So
But I guess it will not work if you don't have Tor like Tor running. So there I guess there is a check that happens in configuration, like when you run configure.ac, it checks whether Tor is available or not. But I'm guessing like probably somewhere that's happening, because it doesn't like automatically deploy Tor for you. So it will need to know somehow that when not to start Tor if you don't have Tor, not you if you don't have Tor running already. Okay, I guess like let's trace back from where we are. So we were talking
yeah,
about, I guess let's go back to the question.
yeah. So there was this connection manager start,
Right.
conman is start. So there they actually you can see the net thread spawning.
Uh
So like the start threads, and like you can see like first you're spawning the thread socket handler.
right.
Like we're
This
only
was the list that we are like looking at.
yeah, and
Uh-huh.
yeah, we're not worrying about all this adcon, opencon. In this PR mainly we are worried about this thread socket handler and message handler. So it's two different layers of the network stack. Like socket handler is concerned with like how stuff are received at the transport, the net layer, and this message handler is one stack above. Like what do you do with the messages you receive? Those
Right.
serialization,
It's
those stuff.
it's the same abstraction difference between net and net processing, right?
Yeah.
Right. Okay.
Message handler is mostly net processing code.
Hmm.
And this net is in our socket handler.
Makes sense.
Very
Okay.
cool. Yeah. Yeah. So we went through it. Like we saw how the threads get spawned in conman start.
Right. Cool. Yeah, that was interesting. So let's go to the next one. What is the difference between net and net processing? I get we touched on it already, and
Yeah.
it's also like described in this PR review club. I guess the first 2 points basically.
Yeah. Same thing we talked about. Like
Yeah.
reads,
So
write messages to the wire, keeps tracks of potential peers, handle active connection to the node.
the main
And this
class is
main,
connection manager, and it's
yeah,
residing in net.cpp.
yeah. Net hands stuff up to net processing, which will read and process all the messages.
Right. So this is like part of the validation engine also, right? Because some kind of some part of like network validation and consensus validation is also, ideally it should not, like that's like the effort to like separate out the validation from net and stuffs, but some part I guess will still be there. And then we have this validation. This is like the validation.h and validation.cpp, which used to be like the historical main.cpp. Like this net processing and validation were combined together into a main.cpp file in the very early version of Bitcoin Core. So that's quite interesting. In one review club, I think we even saw an early version, like the version 1 stuff of it, how the main.file looked like. That was interesting.
I think there is a reading club. Like, we don't have a record.
It was a reading club probably. We don't have a record. It's too bad. I hope like we had a record. I have to see like if, probably true. Yeah, on a reading club. You see.
Yeah. Next question. Yeah. How has the sending logic changed for V1 P2P? Like what's happened to transport class right now?
Right. I guess that's like the gist of the whole PR, like understanding what the
Yes.
PR changed. So let's just get into it. We are also like running out of time for this session, and so I guess like we'll pause a bit for a question round if anybody has, until we go deeper into the code, but we'll finish it in one sitting today. If no immediate question popping in head, then we dive down for the next one and check it out. Cool, let's go ahead.
Yeah. So before we used to have a, like maybe net.h is better for this.
I guess the
Like,
diff tool will be good, or even like the GitHub diff set will be good to understand what changed and why. And I think it's in the commit of, or maybe like just go scan via file in net h and net.cpp. So file changed, not this one, but file changed. And check all the net cpp and net.h. So net.h, I think a little bit smaller to check. So yeah, so this is where it's happening. Like previously we had a transport deserializer. Now we have a simple thing called transport, which is almost the same thing, but simplified and also changed name. So that's the first major thing that happened.
yeah. So
I see pending review comments.
Yeah.
yeah.
So
So this
anything
is
interesting to look at, like anything like noteworthy around the changes that happened in transport? deserializer. I'm also trying to look at the diff set on my end.
I think the sent part completely changed. Like that's the most interesting change.
Mm-hmm.
Like before, like transport, like that's the most important change here, I guess. Yeah, this transport deserialize has the receive stuff happening.
Right. Previously, it
Like,
wasn't there. So, okay, the entire API changed also.
yeah,
So we have some received bytes, we have some set receive version, and set messages to send. So it's not sending directly, it's like setting some message to send. And the doc
yeah,
reads like sending side functions for converting messages into bytes to be sent over the wire. Set the next message to send. If no message can currently be set, perhaps because the previous one is not yet done being sent, returns false and message will be unmodified, otherwise message is enqueued and true is returned. So it's basically handling the sending side of thing to to some QE. Like there is a QE and you add stubs. If it's empty, if it's not empty, then just don't add anything and keep the message
yeah,
intact to be added later. Okay. Then we have some bytes to send, and that's it. That's all the major API of transport. And we have get send memory usage. I guess returns the memory usage of this transport attribute to buffered data to send. So it can like find out a memory usage of a particular message, and
sent buffer.
right,
Yeah,
and
what is in the sent buffer?
whatever is there in the sent buffer, and it will like reserve that amount of space for it. Like I guess that's the purpose of this API. I'm just making it up. I might be wrong, but seems like there is a
Just,
way to get the memory usage of data.
yeah, like before, okay, there's a whole commit on it. Yeah, I can't recollect. Like we'll check into it. Like I'm just telling in a nutshell, like the difference between transport before and versus now. Before, like in transport deserializer, it handled the receiving stuff. So there
Okay.
used to be an API for reading the messages. For like this essentially dealt with reading all the
Right.
header, the payload, stuff like that. And there was also like you could get the CNET message, and
Right.
there was an API for that.
Right.
And right now, like we have the exact same APIs just renamed, and we also had the transport serializer, which had just one function: prepare for transport.
Right.
Like this, yeah, it just essentially had this one transport serializer deals with sending stuff, and that only had one thing called prepare for transport.
Right.
So what
Okay.
prepare for transport did was like you would have to send the entire message immediately at one go. So you need to compute the entire message, and you'd have to send the header, send the payload. There's no pausing. You can't send the first 3 bytes and then later the first 10 bytes. There's no provision for shapeability at all.
Okay.
And when we introduced the new APIs that set message to send, get bytes to send, mark bytes send, all these stuff, like what we essentially get is we have the tools to make the sending side shapeable.
Makes sense. So now you can like hold messages in the midway and send like chunks of them instead of like
Yeah.
sending the whole thing at a one go. Previously, you couldn't break down messages because then like the node, or it's like violation of Bitcoin protocol. So the node will just like reject it. But now we
Yeah.
can have like different chunks of messages sent at different times. So that also means like a single message will be sent in V2 protocol in via multiple chunks.
Yeah, it can be. That's the
Right.
greatest advantage.
Right.
You just keep asking get bytes to send, get bytes to send, and you can like make it shapeable.
Okay. So the transport layer, so this get bytes to send is on the transport layer. So the transport layer is basically um so it's basically ask, so if when you say like transport get bytes to send, it's basically giving you a bulk of byte that you can serialize via either v1 or v2 up to your choice, and
Yeah.
then that will be handled via two different class. One is v1 transport, another, the next one, new one gonna come, will be v2 transport.
Yep.
Makes sense. So that's like the next change after this section is like they introduced a new thing called v1 transport, which is an a parent class, or like how do you know, is a child class or a parent class?
A child
A
class.
child class, right?
Where
It basically implements the transport interface into it. Makes sense. Okay, so that's like the main change happen in net.h. And then there are some mutex that got added inside this uh, inside v1 transport, which weren't there. So later on, when the, if you look at the changes at net.cpp, like I saw like there was some places where it was like asserting lock, and those were like new behaviors and new lock changes that was added. And yeah, so
yeah.
a
And
lot
receive
changed in
mutexes.
net.cpp.
Yes.
Hmm.
Is it just M receive mutex? I thought there's no M send mutex. It should be there, I guess. Yeah, both are there. So
Right.
transport has two mutexes, one for receiving and one for sending.
Right.
It's not strictly necessary in V1 P2P because like I think stuff happen in the same thread, like in the net thread itself. But like I think Sipa wrote some stuff about it. Like we're
Right.
just keeping for class design stuff.
It also like makes sense to have like two separate way of handling it, because if you might want to like spawn them in two different threads, it will need two different mutexes then.
Yeah.
Makes
I
sense.
believe these aren't strictly needed as there's no real way to use this in a multi-threaded fashion. It's
Okay.
just cleaner to make the object responsible for its own consistency.
Okay. Makes sense-ish. And yeah, probably true. Okay,
And then,
what else changed? Viewers message checksum calculation now happens in get message to send guarded by CSV send lock at its call site. Previously, it happened in prepare for transport in push message, which wasn't guided by this lock. Okay, so it's like a various kind of changes clubbed together about like internal handling situations of messages, and you gotta have that, because for the new, it seems like the new design also warrants for a newer way of like abstracting the whole message processing thing, at least in the transportation layers. And that's why we are adding v1 transport and later on v2 transport.
yeah. In sets message to send, like what happens? Like you make the checksum here, the double hash
Mm-hmm.
SHA-256 thing. You
Mm-hmm.
create the header.
Right. And copy the
And
header into C message header. Oh, like copy the checksum size into the header, or how it works?
just the first 4 bytes of the checksum.
Okay.
Like this is 4 bytes.
Mm-hmm. Checksum size
So
4 bytes.
checksum.
Yeah.
So first 4 bytes is the checksum which we use in V1 P2P.
Right.
So we store that in checksum. We store the magic bytes. We serialize the header.
Right. we serialize the network. That's like the network version, or like whether like identifying clear net, or sorry, main net test, network test, those kind of things. And then it goes into a vector writer, and the vector writer takes all this data and do what?
It just puts it into M header to send, I guess.
Message header to send. Okay, so all the header data, it like crafts the header data, puts it into the header data to send, and then some flags are set, and somebody else takes care of the sending part.
M message to send is a C serialized net message. Okay.
So what it's returning? It's not returning anything. This is like a returning bool. So
Yeah, so it doesn't do the serialization itself. Like this just crafts the network packet to be sent.
right. So that's why it calls set message to
Argument.
send, because it's already taking
Yeah.
in a serialized message. So the message has been serialized elsewhere, and it's like it's like making it ready for send. Like whatever is the send QE, put it over there, and you take the basically message byte, like the whole serialized message into it. So
Yeah, so
makes
I'm trying to
sense.
find out where that serialization is being done. So yeah,
Right.
they got
Yeah.
the data from the vsend message queue. So I'm trying to find where,
Mhm.
like, how does vsend message get the stuff?
Right. So it seems like a node vsend message clear. That seems like it's a QE that gets me cleared and push back. And okay, standard message. So where was this message created? Like this message variable, trace this message variable up.
Oh, you get it in push itself.
Okay, so where was push message called? So the call site of push message. Let's find this out. This is fun.
Okay. Oh, so push message actually, like, yeah, it's used for every single P2P message. So they will all take in as argument the CNET message
Message
maker, which we
maker.
looked at. Yeah.
So message maker is responsible for serializing. That's the culprit.
Yeah.
Makes sense. It's a message maker, like a cake maker.
Yeah.
So it has a function called make, and it takes a message type. It takes arguments. Was it supposed to be hard, or we are being stupid?
I think it's all these stuff. Like any optional arguments, I guess.
Okay. Whether compact block version. Makes sense. Whether send compact is true or not. Okay, makes sense. And then what it takes?
It will be different for different messages. So we can't just say it's this type. So I guess that's what.
Okay. Who is taking in the message data? Okay, there is a serialized net message inside as a object inside, or like how do you call it? What is it called in C++? An object, like CNet. There is a C serialized net message called message, right? And it does not
Object.
get set anywhere, right? Or maybe it's setting somewhere as an API of CNet message maker, or I'm making it up. No,
I didn't
it's
understand your question.
let me see if I'm thinking correctly. So there is a function called, like a method called make,
Yeah.
that creates a serialized net message.
Yeah.
So who, like okay, like our Sherlock Holmes question was, who does the serialization and where does the
Yeah.
serialization is happening? So vector
It
writer.
hap-
I think vector writer is something that does it.
yeah. Yeah. That's where it happens.
Okay. Okay, that's where the message data is going, arguments are going, flags are going, versions going, network string is going. Okay, makes sense.
So C serialized net message has these two datas, like a string called message type and the data. a
Right.
vector of unset there. So someone sets the message type,
Mm-hmm.
and someone sets the message data using a C vector writer.
Right. Makes sense.
So
Okay.
yeah, C vector writer is where it happens. Yeah, they have.
C vector writer. What's the doc? Minimal stream for overwriting and or appending to an existing byte vector. Oh, okay. That seems like the guy who would be doing something like that. The referenced vector will grow as necessary. Okay, cool. So C vector writer, that's a constructor. What's their API? Is there any API or like no? I guess that's the API. You just call C vector writer with various stuffs.
Yeah.
Okay.
I guess that answered her. Wait, what is the question?
We
Oh,
were
like
looking
where
at
is?
checksums or something.
Oh yeah, this is a side question, like the one kind of the one you asked in the very beginning,
Right, and
like
it kind
where.
of like we kind of like got in that track, so it wasn't like asking our question, but this happens. So we were like, the second point was like on v1 message checksum calculation now happens in this thing. So it was about the checksum calculation. We actually never looked at the checksum calculation.
Yes.
No,
So
we
we will
did,
check.
right? With like the 4 bytes and all we saw, and then the
Yeah.
vector writer itself writes it to the header.
Ah, okay, yeah, that's where it was happening.
It happens in set message to send. Set message to send is called in socket send data,
Right.
and this is guarded by CSV send. Like if you look at like where it's defined in net.h,
Ah, okay.
they would have written some lock somewhere. Yeah, like see in the call set with lock CSV
Right.
send.
Right.
And even in the net.h socket send data exclusive
Inclusive
lock
lock is
requires CSV.
required. Right.
So if we want to do the checksum calculation, yeah, like we need this lock right now. Before that was not the case because it happened in prepare for transport and push message. Like this prepare for transport was never called in sockets and data.
Okay. So
Like
preparation
right now, set.
happens in set, like before set message to send even called, I guess.
Yeah. Before set message to send. Like it used to happen in push message.
Right. Okay. Which
So
wasn't
is this
guarded by
because
this lock.
Sorry.
right now we can do partial messages, and when we are calculating the checksum, we need the entire one?
Yeah, that's
Is
why
it?
it was moved to the socket send data instead of in set message to send.
Right. I
Okay.
think it will be related. Sounds like it will be related to that thing also. Now that we can have like different ways of message sending, and so and okay, so the send is basically the CSV send is like it's a lock on sending stuff. So you should only calculate the checksum when you are sure that you can send stuffs now. So that's how you have to wait for that lock. Until then, you calculate the checksum.
Yeah.
Makes sense logically. So the third one, what were optimistic and non-optimistic sends? I have no clue.
It's there in the code base. Like optimistic send is like this is which function? Yeah, in push message, like we're trying to send a C serialized net message, right?
Right.
So we made the message and like we have it, like we moved, like we did all this stuff, like we got the bytes to send, and like we have pushed
Right.
it back into the send message queue.
Right. And
So
then we do an
normally,
optimistic send.
yeah. So
So if
normally this
yeah.
sending is done in another thread. Wait, which thread is this? Yeah, it's done in the thread where socket send data is done.
Okay.
So this is push message, and this can be called from like it's actually called, like if you actually trace where all push messages
Mm-hmm.
called, it's like I traced it, and yeah, it's been called from almost all the threads. Sorry, the blue, red, and the yellow. The
Okay.
yeah, push
Blue,
message
red,
is
and
called, and the
yellow. Right. So
yeah,
message handling, add connection, and open connection.
yeah,
So that's where
add
like we
connection and
need
open
to push
connection only the
messages, right? Makes
version
sense.
message.
Okay.
Only like version message for add connection, open connection.
Okay, right. Because message handling will like handle like the responses and rest of the messages and stuff. Makes
Yeah,
sense. Okay.
yeah. So yes, so that means like if you're doing an optimistic sense, like you can directly send it from the message handler thread. Push
Ah,
message is the
okay.
function.
Okay.
So like from this message handler thread, like we are calling socket send data.
Acha. Okay. So that's like the used to be called in another thread. Now, like if it's an optimistic write, then we can push anything from message handler, which was this thread. Like,
Yeah, this could be
oh,
message
oh, it could
handler,
be message handler. Could be message handler.
and it's like we try seeing if there is anything. Like if there's nothing else in the send queue, we immediately send it, because otherwise socket send data is like called uh, this function. Yeah, in socket. Yeah, in socket handler connected, and yeah, like there is some stuff, some timeout all happening.
Hmm.
Like it could happen, and then like we are just delaying it.
Right. Whereas like our QE is empty, we have sent it to some other thread. That other thread is busy with something else and it's just waiting while we could have like sent it right away. So like it's inherently checked by the if clause of like the QE, right? That whenever like the QE is empty, that's when we try to do an optimistic send. Else we do a non-optimistic send. So what's a non-optimistic send case?
The usual case, like we don't send it right now, when like we don't send it just after push message. We wait
Okay.
for all the queue stuff to be processed.
Okay. Makes sense. Makes sense. Okay.
So that happens in a socket handler connected. So this is part of the net thread. So if there's something to send, like you send it using set socket send data.
Makes sense. Okay. But it got cleared in my head as much as it could get. And okay. So what was the last one? What was the last question? What does push message and socket send data do? I guess like we talked about it right now. And
Yeah, we did.
so where does this actual sending happening? So the actual sending is happening inside socket send data, right?
Yeah.
Right. How
But an
does
optimistic push message will call socket send data, right? It's optimistic.
Yeah, push message will call socket send data, and socket send data would send if
right?
socket send data wouldn't send immediately. Like it actually happens here. This is the socket, and
Here you're calling
like
send, right?
yeah. So socket send data actually does the sending with this msock here. If all
Hmm.
these conditions
These
were
conditions are met, right? Some mutex locks are there. So what are the conditions? Some mutex lock and not much. Vsend end is true if iterated not vsend end. So it loops for certain things. Oh, it waits for the vsend the socket like the send QE to get over until it sends, right? So I hope so. I guess so. I'm like guessing from it. If possible, move one message from the send QE to the transport. This fails when there is an existing message still being sent. Wow, some other stuffs are going on. And Here, that set message to send function. So transport set message to send, and then we move on to the next iterator. The iterator is basically node vector message send not until end. So is an iteration over the send QE basically.
Yeah.
And then for each data, we try to do some lock, socket mutex. So we try to hold the socket lock and get bytes to send. Okay, so we got the byte data that is stored inside this data mode and message type. So if not data empty, then if data is not empty, then hold the lock on socket mutex. And if socket mutex locks fails, then break. And then you have, can you just scroll down a bit?
Yeah.
You have a flag, message no signal, message don't wait. Then if more or iterator is at the end, then flag or message more. So like you off the message more flag and then take the bytes and do the socket send.
Off or on?
Um,
We have more to send if either the transport itself has more or if we have more messages to
we have,
send.
oh, I think I read it wrong. So if more or iterator not at send QE end, then message more. Okay, so you set it to true basically, right? So if it wasn't already true, then you'd set it to true.
Yeah.
Makes sense. Okay, and that's like the final send thing while like the data is being written to the socket writer.
Yeah.
That's a long path a message takes from generation to finally going to the network. It's almost like a trek. Okay.
That's it.
Yeah, go ahead.
That's it.
Yeah, so we did completed all the questions. So congratulations, we are like extra 20 minutes, so we'll not extend it further. And but this was good. This was really interesting and a nice deep dive around the core. So I hope like we had fun. I hope whoever is watching will also have fun. So let's have like last one round of like conceptual, technical, or any other kind of question, and then we'll call it a day.
What's one takeaway from this entire session?
I think my main takeaway is like I'm excited about the new improvement that is happening in the message handling, both code wise as well as structurally, as well as the new things like the V2 protocol that is coming on. So that's pretty exciting. And second takeaway is message handling is complicated.
We didn't go to message handling. We were
Oh, we
just in a
didn't go
net
to message
thread.
handling. We are just like the very base layer of message. We just received the message, right? We don't even know how to read it yet. We just received the message, and that itself goes through a lot of checks and stuffs. But that's good. Like that's kind of like shows the intensity of the stuffs that goes on around Bitcoin Core. Okay. Any question? I don't think I have any question as of yet. I'll still think about the whole thing and pass it around one more time. And if I have some question, I'll post it in the channel. But
Yeah.
that's it from me so far. Okay, so I guess that's it, and we'll call it a day. Thank you, everybody, for joining in. Recording will be published soon, and we catch you guys next time. Same thing, same time, 2 weeks later on Thursday, 8 o'clock IST.